Hi everyone, I am Sachin. I am the co-founder of AccelerateAI. At AccelerateAI, we want to help you accelerate your career in artificial intelligence and data science by helping you learn about topics which are relatively less known but could be very, very powerful. So today we are going to talk about a similar topic called quantile regression. It's a relatively lesser known regression technique. We'll cover the need for looking beyond ordinary least square regression and why do we need quantile regression. Then we'll talk about the formulation of quantile regression. I'll also cover some of the advantages of quantile regression over ordinary least square regression. And then I'll also show you some sample problems in Python to concretize the concepts of uh, quantile regression. So let's get started. Consider a situation where a bank is trying to understand and then be able to predict a key metric for them, which is the customer lifetime value. Let's say an analyst pulls out some sample data of about 500 customers and then wants to study the relationship between customer lifetime value and the maximum balance of the customer account. So the data will look something like this. As we can observe, the customer lifetime value here is on the y-axis and the maximum balance is on the x-axis. The data seems to show an increasing trend in CLV with increase in the maximum balance. However, we can also observe that this data is not normally distributed. The variance increases as the maximum balance increases as well. So the standard deviation is not constant, or the variance is not constant. This kind of data, as you might know, is called heteroscedastic data. Ordinary least square regressions cannot be used here to predict the CLV because the error terms will be not normally distributed. One way to solve this could be to take a transformation on the y-axis. So if we take a log transform on customer lifetime value and then plot the values again, this looks something like this on the right hand side of the chart. Now, someone might argue that we can fit a ordinary least square regression on the transformed value of y. However, understand that this kind of a transformation will not preserve the expected mean of the y variable. And in linear regression, what we try to get is the expected mean conditional on all of our x's. Let's look at another example. So retail stores are very heavy users of data science and machine learning. A retail store chain is very interested in understanding the close rate. Close rate is the percentage of shoppers who would go into a retail store and then end up buying something in that store. It's very important for the management to understand the factors that are responsible for the close rate. So, an analyst or a data scientist working for a retail store would collect various different variables to understand the relationship between those variables and the close rate. Let's say we capture information around the general characteristics of the store, like the total square footage, the number of people working there, where the store is situated, is it within the city center versus outskirts, and so on. Also important are the promotional activities running in a store, the discount, sales, advertising spend, and so on. So we collect all of this data for multiple stores, and then we want to understand how is the close rate dependent on these variables. Now the close rate, as we can guess, will not be a constant for a given set of variables, and there will be a difference or a variance around that. So there could be questions from the management like how can I predict a high close rate such as the 90th percentile of the close rate distribution. What we are also interested in very importantly is those variables which could explain a low close rate such as the 10th percentile, and what can we do about increasing the uh, close rates in those cases. Also, are there variables that differentiate between a low close rate and a high close rate? So these are very important questions to be answered where we are interested in not just the mean value, but also the distribution of the close rate. Let's take another example in financial risk management. Financial institutions and regulatory bodies oftenly use a concept called value at risk as a measure of market risk. Value at risk is the amount of money a portfolio could lose within a given time period. It's usually within a specified confidence level, like 1 minus alpha, where alpha is a small value, like 1% or 5%. So here, what we are interested in is these lower extreme values, and we want to understand what are those lower extreme values. Now, again, a standard method like ordinary least square and even something like Arch will not be able to help us here, because Arch also assumes normality of the data distribution. So we have seen in one of the previous videos, there are common issues with multiple logistic regression. If you want to refresh your memory, you can look at one of my previous videos where I have talked in depth about some of these issues caused by heteroscedasticity and presence of outliers for multiple linear regressions. So what happens in a game when one of the player is not able to perform well? In such situations, what we usually do is we try to bring in another player to rescue the game. So something similar happens in these kind of extreme situations, or when the data is not normally distributed, where we cannot use ordinary least square regression. So we bring in a different kind of a regression called quantile regression. It's not very different from ordinary least square regression, but there are certain advantages, and we'll see that. So how do we formulate the quantile regression? Let's first understand ordinary least square in order to then understand the difference. So in ordinary least square regression, we want to minimize the mean squared error, and in doing so, we get the parameters or the coefficients uh, in the data, which gives us the equation y equal to beta naught plus beta 1 x1 and so on. Now understand that this y value that we get is the conditional mean or the expected value of y. Obviously, y can vary from one observation to the other for the exact same x variables as well. Another way to look at this is what is called as least absolute deviation regression. In least absolute deviation regression, instead of looking at the squared of the error terms, we minimize the modulus of the error terms. Square or the error terms heavily penalizes the outliers, and hence, as an alternative, least absolute deviation could be looked at, where it is the absolute value of the error term and not the square. Now, if we minimize this to get our parameters beta, this will give us these betas, but the value of y that we get is not the expected value. Here, what we get is the median value of the y. Some situations, this is a good thing because expected value or the average could be swayed away by outliers or by skewed data, whereas a median is a much robust um, measure of the central tendency of the data. Now, an extension of least absolute deviation regression is called quantile regression. In quantile regression, we again use the absolute value of the error. However, there is a weightage given to those errors depending on whether the error is positive or negative, which means whether the value is overweight or underweight. So in quantile regression, we want to minimize the sum of errors in such a way that we give asymmetric penalty or weightages to these under prediction and over prediction. So for under prediction, we multiply it with the q, where q is the quantile. And for over prediction, we multiply it with 1 minus q times the modulus of the error. By minimizing this particular sum of errors, we will get these betas. Now these betas will be dependent on the quantile that we are looking at. So if you are looking at the 10th percentile versus the 90th percentile, the betas will be different. So here what we get is the y value which is at that particular quantile. And the betas, as I said, will be dependent on the quantile itself. So for different quantiles, we'll get different values of beta. Let's try to understand it a little bit better. So as I said, in order to find the smallest mean absolute deviation, we multiply the error terms with the weights. So the equation is when y is greater than the expected value, we multiply it by q times the modulus of the difference. And when y is less than the expected value, which means this is a negative term, we multiply the modulus of the error term by 1 minus q. Sometimes this is also written as a function rho of tau times this error term, where rho of tau is tau times the max of r comma 0 plus 1 minus tau times max of minus r comma 0. So when r is positive, we get this term becomes 0. And when r is negative, this term becomes 0 and this term becomes positive, and we multiply it by y minus tau. So here our tau is the quantile that we are looking at. Now this function is also known as the check function, because when we plot this with this as the slope tau, the um orthogonal vector here will become tau minus 1. So this looks like a check function, and that is why it's called a check function. Let's try to understand this by an example as well. So if you are interested in the median of the 10th percentile, we'll have 90% of our errors as positive. They are higher than that particular value of the 10th percentile, and 10% of the errors will be negative. So in such a case, what we'll do is we'll add a weight of 0.9 to the negative errors and a weight of 0.1 to the positive ones. And then we can expand this for a given quantile and try to solve for the betas. Now this particular function is non-differentiable, so we cannot use calculus to get the betas. What we do is use some kind of a numerical method. So coefficients for quantile regression will be computed using simplex method. The good news is that it is guaranteed to yield a solution in a finite number of iterations. So we have talked about how to get the betas for quantile regression. Now, what are the advantages of doing so? So let's look at that. In ordinary least square, we predict the conditional mean. And as we have seen in terms of heteroscedastic data or a lot of outliers, the mean can be swayed around. It's not a good measure of the central tendency. In quantile regression, we are predicting the conditional quantiles. And the quantiles are a much better way of understanding the distribution of the data. In ordinary least square, one of the important assumptions is the assumption of normality of error. So if error terms are not normally distributed, the values that we get and the inferences that we make from ordinary least squares will not be correct. In quantile regression, the good news is that it is distribution agnostic and hence is generally used when the data is not normally distributed or the error terms are not normally distributed, to be very specific. Ordinary least square will be sensitive to outliers as well, whereas quantile regression is robust to these outliers, both for the response variable as well as the x variable as well. We also talked that in ordinary least square, we are getting the expected value, and expected value is not preserved under transformations of the y value, like log transformation. In quantile regression, that is not the case. It does preserve the quantile value under all of these kind of transformations as well. Now, the advantage of ordinary least square regression is that it applies when n would be small, maybe 20 or 30 data points for a given variable. We'll be able to calculate the betas with good accuracy and precision. Whereas for quantile regression, we'll need sufficiently large amount of data because we are looking at calculating these betas for different percentiles. Ordinary least square is also computationally inexpensive because we have a closed form solution and a formula for it. Whereas for quantile regression, it is computationally intensive. It takes a little bit of time, but with modern day software and computers, it's not that big of a deal. However, it uses numerical techniques and hence slightly more uh, time taking than ordinary least square regression. So we talked about all of this. Now what we can do is look at an example of quantile regression and in Python and try to understand what this means. So let me bring up the screen. All right, so we will look at the quantile regression example. Quantile regression is in stats models. So we will import stats model API as well as the formula API in here. For this particular example, I will use a famous data set called food data set. This is something that has been very common in econometrics. The there are two variables in here, the food expenditure of a family or a household and the income of that household. And what you are interested in knowing is how does the food expense vary with the income of the household. Now, the income will not be normally distributed as we can understand. There will be certain households, or most of the households will have low to medium income, whereas there will be certain households which will have a very huge or large income. And then we want to understand how does the food expense vary there. So let me plot this data and show it to you how it looks like. So here is how the data will look like. On my x-axis, I have income, and on my y-axis, I have the food expense. As you can see, there is heteroscedasticity in the data. In order to build a quantile regression, the function is called quantreg, and we provide the data in form of a formula. So food expense tilde income, or food expense as a function of income, is what I'm interested in this particular quantile regression. I fit that model and I want the quantile regression at the median, or quantile equal to zero 0.5, and then I print the summary of the results. So here is how it looks like. It's not very different from the results we get in ordinary least square regression. So it tells me that my pseudo R squared is about 62%. We have 235 observations. There is only 1 degree of freedom, which is our income. And then it gives me the coefficient of income as well as the intercept. It also gives me the t value and the p value as well. And as we can see from the p value, both of these are statistically significant. It also tells me that there might be strong multicollinearity, but we can ignore this because we only have one variable here. Now, if you want to visualize this result, what this means, what we can do is create these regression equations for multiple quantiles and then see how it varies. So that is what I'll do here. I'll run the model quant regression for multiple quantiles, 0.1, 0.2, and so on. So for all the deciles, I've written an equation here so that I can collect all of the parameters, the intercept and the income, as well as the upper and lower bound of the 95% confidence interval for the coefficients. And then I'll aggregate all of this into a pandas data frame so that it's easier for me to look at. For comparison purpose, I'll also build a OLS regression. So once doing that and printing this, here is the results for the quantile regression. So for various values of quantile, the first decile, second decile, and so on, you will see that the intercept as well as the coefficient beta varies as the quantile increases. And this is the upper and lower bound of the values as well. If we compare it with the ordinary least square regression, we get the coefficient is 0.8485, which is somewhere in between these. So in OLS, we get just one beta, whereas in quantile regression, for each quantile, we will get different values of beta. So if you are interested in the median value, then we'll use this particular equation. So quantile regression will not only give us one value, but it also helps us understand the distribution of the data. What's the 10th percentile look like, or what is the value of the 10th percentile for a given X variable? What's the 50th percentile of the value for the given X's, and so on. Another way to look at this is, we can plot these different regression lines and then look at how that varies. So I'll do that. I'll plot all of these in one particular plot, and then it's easier for me to compare it. So here's what I have done. The red line indicates the ordinary least square fit of the line, and all of the light gray lines in dotted lines show me how the quantile regression lines look like. So this is the 90th percentile value, this is the 10th percentile value, and so on. And as we can see, the slope changes with the percentile as well. Another way to look at quantile regression and understand is try to understand how does my beta change with the quantile itself of the given X variable. So again, I can plot that, the betas for the different levels, and here is how the betas will change. So the blue is my quantile regression beta and the 95% confidence interval shown by these dotted blue lines. And for my ordinary least square, the beta is constant across the different quantiles with the 95% confidence interval. So you'll see that only in a small region here, ordinary least square is overlapping with the quantile regression betas. Whereas in all the other regions, my beta is slightly different. So the quantile regression point estimates will lie outside the OLS confidence interval for most of the cases, which suggests that the effect of income on food expenditure is not constant across the distribution. So it changes with the distribution itself. So hopefully that was helpful in understanding, how to build a quantile regression model and how to interpret the results. Quantile regression is quite common. So we often encounter these kind of heteroscedastic data. It's not that rare as one might initially think of. Quantile regression is very heavily used in healthcare, where we are interested in understanding, let's say, the growth of a child, and we are interested in knowing whether the child is malnutrition or whether the child is obese. So these are the extremes that a healthcare professional will be interested in. Quantile regression is very heavily used in economics as well. There is a distribution of, let's say, GDP growth or economic indicators across countries, and we are interested again in knowing the extremes and how our variables are impacted in those extreme cases. It is also used in standardized tests like the IQ test and so on, where we are interested in ranking people based on certain standard criteria. I talked about finance, it's heavily used in finance, also in retail, where we are interested in, again, not just the mean value, but also looking at the distribution. We'll use quantile regression. So quantile regression could be a very, very useful technique for you to know and use it in your next project and impress your boss. So I hope this was all helpful. Again, thank you so much. I am Sachin from Accelerate AI. If you do find this video useful, uh, please go ahead and subscribe to our channel. You can also check us out on LinkedIn at Accelerate AI and write to us on acceleratedatascience.com if you have any queries. Thank you so much. I hope this was helpful.